All right, children, so here's our lesson 4-1 video. Here's a glimpse of our do now. Pretty straightforward. Shouldn't need to get any hints there. And if need be in class, I can give you some hints. Anyway, so let's dive right in. So this lesson is about piecewise defined functions. Our EQs are how do we graph them, and how do we express the domain and range of functions using interval, inequality, and set notation. And when I write the word parenthetical, well, you'll see what I mean here later. Little FYI here at the bottom, graph paper is going to be pretty good to have. If you don't have it, you can print it using or downloading some stuff I shared with you on Google Classroom. It's under the ebook topic, okay? And there's actually little grids that you can print out. If you have no way of getting to that, let me know. Obviously, here at the school, we can hook you up with some graph paper. You can come and pick some up from the office if you absolutely need to. Without further ado, here's our actual lesson. So basically, piecewise is exactly what it sounds like. It's going to be functions that are in pieces. So in class, I would actually have you work as groups to go ahead and look at these two functions graphed side by side like this, kind of conjoining. So on the one hand, we've got y equals x minus 2 for x less than 3. So here's x equals 3, right? And x less than 3 is talking about everything to the left of 3. On the other hand, we have y equals negative 2x plus 7 for x greater than or equal to 3. So that's this guy here going off to the right. So we've got this equation for x equal to or bigger than 3, and we've got this equation for all x smaller than 3, right? So how could we describe this as completely as possible? Well, to put it simply, what is this? Okay, so obviously it has both a positive and negative slope. That's one weird thing we can say. Another thing we can say is, well, that our slope is positive, right? Our slope is positive for x less than 3, and our slope is negative for x greater than or equal to 3. Another thing we can say is, well, is this technically linear? I'm going to go ahead and say that it is linear. Okay, you could argue either way there. Okay, so number 2 is what I keep itching to say here on number 1, but let's go ahead and save that for number 2. So is this graph a function? So you're pretty much being told, yes, it is a function, but why is it a function? Okay, so this graph, simply put, is a function because I can draw a vertical line through it. Okay, if I can draw a vertical line through it and it never intersects the graph of the function more than once, okay, then it is a function. Okay, so we would just say it passes the vertical line test. Okay, that'd be the simplest thing to do. Okay, so another reason, and we would have to look at a table for it, but this is really the simplest way to tell is when you graph it, if you can draw a vertical line through it. We'll talk a little bit more about what all that means here in a second, here pretty soon actually. So let's go ahead and graph, and if only I could get that out of my screen, let's go ahead and graph y equals x squared minus 3. Okay, so let's make a table here. So I'm going to make an input-output table, or a T-chart, or whatever it is you learned that this was called. Okay, so I'm going to start, so this is for x less than or equal to 0, right? So I'm going to start out here to the left. Let's say I start at, let's start with something small. Let's start with negative 3. Not even, that won't fit on here either. Let's start with negative 2 then. So at x equals negative 2, I would have negative 2 squared, which is 4, right? So I would say y of negative 2 is equal to negative 2 squared minus 3. Negative 2 squared is going to give me 4 because a positive times a positive is a negative times a negative is a positive. Okay, and I'm going to get 1. So when x is negative 2, here on my blue function, when x is negative 2, y is 1. So that's going to be my first point that I'm going to graph. Okay, what about negative 1? Well, same idea. So now I'm going to do y of negative 1 instead, right? Y of negative 1 instead, and that's going to be negative 1 squared plus, oops, not plus 3, minus 3. Okay, and that's going to give me 1 minus 3, which is going to put me at negative 2. Okay, and now let's try 0, which is where we're going to stop because x is less than or equal to 0. So we're going to look at y of 0. 0 squared minus 3. That's going to leave me with just 0 minus 3, which is negative 3. Okay, so I've got y is negative 2 at negative 1, and at 0, y is negative 3. Okay, and this is a dead giveaway that this graph is going to be curved and nonlinear. It's going to be a parabola. Little review there from Algebra 1. Didn't see any of that in geometry, but you did see this. You did see parabolic functions in Algebra 1, so that's not new. Okay, and we're going to do likewise for this guy over here. Okay, so y equals 1/4 x plus 1 for x greater than 0. Okay, so same idea. Let's make a little input-output or a t-chart, and we'll start at 1. Okay, because x is greater than 0. We are not including 0, so we're going to start at 1. We're just going to use integers. Okay, whole numbers. So at x equals 1, we've got 1/4 times 1. Let me go ahead and write out the function notation. So we're doing y of 1. Okay, so 1/4 times 1 plus 1. And that's going to give me 1/4 times 1 is 1/4, plus 1 is going to give me 5/4. Okay, so that would be 1.25. So at x equals 1, we have 5/4, also known as 1.25. Okay, so at x equals 1, we're going to go ahead and say 1.25. It'd be about right there. Let's go ahead and get an idea of where it would be at 0, because we wouldn't include 0, right? But where would it start? Here. Okay, so if I go ahead and plug in y of 0 instead, erase and give myself some room. So y of 0, 1/4 times 0, 1/4 times 0 is 0, and then that plus 1, that's just going to give me 1. So 0, y is 1. Okay, so we're starting here, and this would be an open circle. Okay, this would be an open circle because of this guy right here. X is bigger than 0. We are not including 0. So let's keep that in mind. Anyway, let's go ahead and look at 2. So now y of 2 okay, so that's going to give me 1/2 plus 1. So that is going to be 3/2, aka 1.5. So at x equals 2, I'm going to be at 1.5, which is right about there. Okay, let's go ahead and plug in for 3. And you can tell this is getting a little bit tedious. Okay, but that's only because, well, we kind of have to right now because this graph is really small. But let's go ahead and erase, give ourselves some room again. So 3. So that's going to give me 3/4 plus 1. And that is going to give me 7 over 4, otherwise known as 1.75. So 7/4, aka 1.75. And we're just increasing, it looks like, by 0.25 each time. So we're at 1 3/4 now, getting closer to 2. And at 4, well, if we do y of 4, 1/4 times 4 plus 1, that's going to give me 1/4 times 4 is going to give me 1 plus 1, and obviously we know that's going to be 2. Okay, and this guy's going to continue on just like that. Okay, so this is how our graph is going to look. Okay, now, again, in your groups, which you can't do if you're watching this video, I want you to describe this as completely as possible, just like you did on item 3. So this particular graph, is it a function? Let's answer this real quick. Is it a function? The answer is yes. Why is the graph a function? Because again, I can draw a vertical line anywhere on this guy, and it'll never intersect the graph more than once. Okay, so it passes the vertical line test, just like the last one did. Okay, so what are some things we notice about it? Well, for x less than or equal to 0, we can say it's nonlinear. So that kind of means the whole thing is nonlinear. Okay, there's a positive slope for x greater than 0, right? There's a whole number of things that we can say. Okay, and I'm not going to dwell too long on that just for the sake of time. So the functions that we looked at in items 1 and 3 are called piecewise defined functions. Okay, they're piecewise defined functions. So let's look at the function from item 3 as an example. Okay, so the function from item 3 was this guy. Okay, so actually, no, it wasn't. It was this guy. I'm an idiot. So we've got y equals x squared minus 3. So y equals x squared minus 3. And that was for x less than or equal to 0. Or we say if x is less than or equal to 0. And then if x was greater than 0, we would say that it's 1/4 x plus 1. Okay, now, if we're going to truly call this a function, we would say f of x, right? That's just a fancy way of saying y depends on x. Y is a function of x. Okay, that's all we're saying here. And we're saying that f of x, or y, is going to be equal to whatever x is squared minus 3 if x is less than or equal to 0. Okay? And we are also going to say if x is bigger than 0, that 1/4 times whatever x is plus 1 is going to give us our y value. Okay? So it's kind of like we've got some conditions to look at. So these guys here are kind of like constraints from when we were talking about systems of inequalities. Okay, but the more proper word that the book wants you to use, and let me look and double check here, it wants you to use the word domain restrictions. Okay, so these guys here are domain restrictions. I'll use a different color to try and. These guys here are domain restrictions. Okay, so the x is less than or equal to 0, x is greater than 0, those are restricting your domain. All right? These guys right here, it's wanting you to call your function rules. Okay, so that's this guy and this guy. These are your function rules. And your function rules depend on your domain restrictions. It depends on where you're at on the x-axis, and that tells you what rule to use. Okay? And obviously, this guy over here, the book just wants you to know that this is just literally the name of your function. It's pretty straightforward. So now we've got another example of a piecewise. And we are going to go ahead and fill in the table and graph it out. So let's read what we've got. So g of x, that's the name of our function, right? G of x is equal to negative 2x minus 2 if x is less than negative 1, or it's equal to x plus 3 if x is greater than or equal to negative 1. Okay, so our key point that we're looking at is x equals negative 1 right there. Okay, that's where the rules change. All right, so let's start with less than negative 1. So that means we're going to go up to this point, and I'll do this in red. Okay, so negative 2x minus 2. So we're going to do g of negative 4. That means we're going to be using this rule here in red because we are less than negative 1, right? So negative 2x minus 2. So negative 2x minus 2. Okay, and that is going to give me 8 minus 2, which is 6. So that guy is just 6. So we have negative 4 by 6 right here. Okay, and let's do the next one. And really, you could cheat a little bit. Our y-intercept is minus 2 for this guy, and our slope is also negative 2. So if I just count plus 2 and minus 1, okay, so here we're going to be exclusive here with red. Red is going to be exclusive because of this guy here. It's less than, right? So that means we are smaller than negative 1. And I'm just going to keep counting with the slope. I'm going to cheat a little bit just for time's sake. So this guy is just a linear function. Looks just like this. Okay, and I just counted it out using the slope and the y-intercept. Okay, something we should already be pretty familiar with. So at x equals negative 3, we are at positive 4. And at x equals negative 2, which is right here, we are at 2. Okay, so that's a little bit faster than just plugging in things like this over and over and over again. Okay, so using blue now, I'm going to go ahead and start here. So I'm going to start at, so now we're looking at this guy here. We're using this rule here in blue if x is greater than or equal to negative 1. Okay, so let's look at where we would be if x is greater than or equal to negative 1. So we're going to say g of negative 1. That means we're using the blue rule now. Okay, so x plus 3. That's just going to give me that g of negative 1 is positive 2. And that's going to be right here. And we're going to use a closed circle because, again, this is greater than or equal to. So we are including x equals negative 1. Okay, so that's going to give me a 2. And we're going to cheat a little bit again. Our y-intercept is 3. Okay, our y-intercept is 3. So that means that x equals 0. Our y is 3. And if we just keep counting, our slope is 1. So we're just going to go up 1 over 1. Plus 1, and so on, and so on, and so on. So that's what our piecewise function is going to look like. Okay, and if we go ahead and finish the table, so 1 gives us a value of 4, and 2 gives us a value of 5. So pretty straightforward. That's all there is to this, guys. And if you have graph paper, I mean, you can follow right along with this. So looking back at item 5, Esteban says g of negative 1 equals 2. Is that correct? Well, all we have to do is look back at what we've got. is g of -1 positive 2? And the answer is yes. We know that's true. We can explain it by just saying, I mean, 2 is greater than -1, so that means it's following the rule. So 2 is greater than or equal to -1, so g of x is equal to x plus 3, right? And if we do g of -1, which we actually did that earlier, it gives us 2. So Esteban is absolutely correct. Okay, how do we graph a piecewise defined function? Well, I would start out by making a table, whether you call it a T-chart or an input-output table, that's up to you. But start by making a table for certain values, right? And follow the function rule matching your domain restrictions. It's the simplest way to put it. And you just graph according to the table. You just graph your ordered pairs based off of that. So that's our little process. If a piecewise defined function has a break, how do you know whether you use an open circle or a closed circle? So looking back over here, in red we have an open circle, in blue we have a closed circle. Well, why is that? Well, if we look back at our domain restrictions, so here in red again we see x is less than. It is not equal to -1, it is less than, so we don't include it. That means it's open. Now, here in blue, our blue restriction, x is greater than or equal to. That means we include -1, so that means it's closed. Okay, so that would be how we answer number 8. So let's talk about domain and range. So the domain of a piecewise defined function consists of the union of all the domains of the individual pieces of the function. The range is pretty much the same idea, except, well, so let's go ahead and let's do some color coding again. So when we're talking about domain, domain is x, right? This is domain. Okay, now range, when we're talking about range, we're talking about y. Okay, so your domain is basically put, in teenager speak, everything x is or can be. Okay, and your range, again, in teenager speak, is the exact same thing. Everything y is or can be. That's the simplest language I can put that in. Okay. Now you can represent your domain and range in a number of different ways. You can use inequalities, you can use interval notation, and you can use set notation. Okay, and we're going to see more or less how to do all of these. So here we're looking at our graph from earlier. It's the exact same graph, except drawn much prettier by the book, not all butt ugly like the way I did. And here is our function again from what we just did earlier. Okay, so write the domain and range of g of x from item 5 by using, so if we use inequalities, let's use inequalities first. Okay, so our domain, if we're using inequalities, we're talking about x, right? So what is everything that x can be? Well, we would simply say, if we're using inequalities, that x is somewhere in between plus or minus infinity. X can literally, if we're looking at the x-axis, X can literally be anything on this x-axis, going on and on and on and on and on and on and on. Okay, so X can be literally anything, right? What about our range? What about our range? Well, that's a little bit different. Okay, so let me erase a little bit. So our range is a little bit different. Can we say that our range is somewhere in between plus or minus infinity? No, we can't. Okay, but what we can say is that y is anything above the x-axis. In other words, y is greater than 0. Are we including 0? No, because we have an open circle here at y equals 0. Okay, so this would be our range using inequality notation, right? So now looking at interval notation. Okay, and interval notation, the book is calling it interval notation. I call it parenthetical notation. It's the same crap. But basically, all we're going to do is take this and basically rewrite it using parentheses, right? So the way that we're going to do that, and I actually misidentified this. Nothing, we shouldn't say less than or equal to infinity because that's impossible. Okay, we cannot include infinity. Okay? Infinite, you can't say something equals infinity. You can say something is infinite, meaning it has no finite value, but you can't say something is equal to infinity, right? That's not possible. So, yeah, we need to have just x is greater than negative infinity, or it is less than positive infinity, okay? And that was a goof on my part. But anyway, the way that's going to look in interval notation here, so let's look at our domain. So our domain, again, is x, right? So if we rewrite this, we would just use a curved parenthesis, a curved bracket, like that. And we would say negative infinity, comma, positive infinity. And this basically means the exact same thing. The exact same thing as what was up here with our inequality notation. Okay, it means the exact same thing. What about our range? Well, our range is simply this. So we are not including 0. We're not including 0, so we leave this a curved bracket as well, right? Because when you have this guy right here, that means you have a curved bracket. You have a curved parentheses. Okay, so from 0 to, well, y can be positive infinity, right? So another way, and here, I like using 3 terms. Another way we could have used the inequality notation, we could have said that 0 is less than, y is less than infinity, okay? You also could use what I used a second ago. You could say that y is simply greater than 0. Either one of these is correct, okay? They both mean this here. They both mean this here. Okay, so that's what's kind of wishy-washy about this. So now with set notation. Okay, so this is a little bit crazy. Okay, so set notation, and let me double check with the book because depending on what book you're looking at, set notation can change a little bit. So this set notation the book is using is a little different than what I learned. Okay, so set notation, again, I'm representing the exact same thing except using what's called set notation and not using parentheses, not using inequalities. I'm going to say that I'm going to use a curly bracket, okay, as best as you can draw one, and you're going to say x or domain. So when you write an x right here and then this bar, this is saying that you're talking about domain because you're talking about x, okay? So your domain, basically, or your definition of what x is, you're going to say x is on or is an element of the set R, okay? And we'll have to elaborate a lot further. I'm not going to go into it on this video, but I am going to elaborate on this further probably in the next lesson or in a separate video. But basically this R right here, it stands for real numbers, okay? It stands for real numbers, right? So that's all I'm going to do for this one. I have a hard time drawing curly brackets on the right. Anyway, so what we're saying is our domain is that x is a real number, or you could say that it's all real numbers. X is all real numbers. Okay, that's basically what we're saying with this monstrosity. Okay, now our range is going to look pretty similar. Our range, so y denotes our range, y bar like this. We're talking about our range. And y is an element of the real numbers also, but we have a second limit, a second little limitation, and that is that y is greater than 0. So we put a little comma, and we say that y is greater than 0. So our range is simply that y is a real number that is greater than 0. And again, I feel like I didn't say that quite correctly with the domain. Our domain is simply that x is a real number, and that's it. X is a real number, meaning x can be all real numbers. Okay, so let's look at a few more. Let's look at a few more examples, and these I'm going to have you do on your own in class. For the sake of this video, and let me see how long I've gone over. Yeah, I'm already at 30 minutes. So I'll leave these for you to do as an exercise on your own. If you need help with this, come to me in tutoring. Okay, but yeah, I don't like making these videos longer than 30 minutes, and I'm already at 31 minutes. Okay, so the domain of a function, so we're doing our check for understanding here, part 2. The domain of a function is all positive integers. How could you represent this domain using set notation? Okay, so how could you represent this domain using set notation? So the domain is x, and we're using set notation. So curly bracket x bars, because we're talking about domain, right? And it's all positive integers. Okay, so that means that x is an element of z, set z. Okay, and I guess I'll go ahead and go over all of this here in a second. But let me go ahead and finish through this example, and we'll go over the actual sets. If you don't remember, you learned this in Algebra 1, I believe, briefly, but I don't know how much you remember, so I might need to do a separate video where I go over the number sets. Okay, so all positive, so there's another key, right? Here's another constraint. So here's a limit, so it's an integer, right? It's an integer, but it's a positive integer, all positive integers. So we're going to say that x is greater than 0. Okay, interval and set notations represent the range y is greater than or equal to 3. So let's start with, so interval is our parenthetical notation. We're going to use parentheses. Let's start there. So our range of y greater than or equal to 3. So we're going to say, actually, so this is a good example that we need to see. We have greater than or equal to this time. That means we include 3. So we're going to use a square bracket. That means we're including 3, comma, and everything greater than or equal to 3. So that means infinity. Okay, and basically what I'm saying here is that 3 is less than or equal to y is less than positive infinity. Okay, that's what this interval notation means right here. Okay, but when we say interval notation, we're talking just about the parenthetical. Excuse me. Okay, now set notation. So if we're doing range, we're going to do y bar, and we can't forget our little curly bracket. And y, it doesn't specify, so we're going to go ahead and assume that y is a real number. It's on the set R. Okay, and we're just going to add in the specification that y is greater than or equal to 3. Okay, and all of these in pink mean the same thing for this guy here. Okay, what can you conclude about the graph of a piecewise defined function whose domain is that x is a real number and it doesn't equal 2? Well, basically, that x is, how could we word this? So x is greater than 2, and x is less than infinity, right? We can say that. And we can also say that x is less than 2 and x is greater than negative infinity. Okay, and the way I would rewrite that, because I don't like having my inequality symbols facing that way. I'm a little OCD that way. The way I would rewrite that, I would start over. I would say negative infinity is less than x is less than 2, or 2 is less than x is less than positive infinity. Okay, and what we're doing there is basically excluding 2. X does not equal 2. And x is all real numbers otherwise. Okay, so really quick, we've got an important type of piecewise function. Okay, and what this type of piecewise function is called a step function. Okay, it's called a step function, and you're going to see why here in a second. Okay, so f of x equals negative 2. I'm going to try and color code here. F of x equals negative 2 if x is less than negative 3. So x is less than negative 3, and it's equal to negative 2. So basically, it's going to look like this. We're going to have an open circle, right? And we're going to have just a horizontal line going off to negative infinity. And we're not going to include negative 3. Right? And then let's look at this next constraint. And I'll do this one in red. So f of x, or y, right? Remember, this is a fancy way of saying y is equal to 1 if x is greater than or equal to negative 3. So again, we're here at negative 3. And less than 2. So stopping at positive 2. So that means we have an open circle at negative 3 at y equals 1. Or I'm sorry, a closed circle, because we're including x equals negative 3. And we're going all the way over here, another horizontal line, but we're going to do an open circle here at x equals positive 2, because we are not being inclusive with that positive 2. And our last one, y, or f of x equals 3 if x is greater than or equal to 2. So y equals 3 if x is greater than or equal to 2. So we're going to use a closed circle because we're including, and we're just going to go off to plus infinity out this way. Okay, and you can see why it's called a step function, quote unquote, because we have steps, right? It steps its way up. Okay, you're not going to see a whole lot of these, but it's just good that you know what it is. So if you ever hear the word step function, this is what it's talking about. It's just a piecewise. It's still just a piecewise, but you've got horizontal lines. Okay, you've got constant values of f. And what do I mean by constant? Well, negative 2 is a constant, right? There's no variable. It's just negative 2. It's constantly negative 2 here. It's constantly positive 1 here, and it's constantly 3 here. Okay, so here's our EQs again. And this is the point where you're going to want to start your lesson 4-1 practice. Hopefully I didn't go too long on this video. And if I did, I apologize. Yeah, I'm at 39 minutes. So I'll go ahead and cut it off here. Obviously, if you have any questions, shoot me an email, and have a nice day. Goodbye.